The secondary amperage rating of the transformer, 1200 plus amps, indicates the maximum load current that the transformer can handle. To protect the transformer and downstream equipment, fuses must be installed on the secondary side with a rating below 1200 amps. The 1200 amps rating of the 2300 volt switchgear bus means that it can safely carry up to 1200 amps of continuous current. However, this rating does not prohibit installing fuses with a lower rating on the secondary side of the transformer. A recommended fuse arrangement to protect the transformer and equipment while meeting the switchgear bus rating involves installing 6 400 amps fuses downstream of the 2300 volt switchgear bus. Connect each fuse to one of the 6 incoming feeds from the transformer secondary. Install a main disconnect switch upstream of the fuses to isolate the transformer from the incoming feed. The fuse rating should be selected based on the load current of the downstream equipment. For general loads, fuses with a rating of 200% to 300% of the load current are typically used. In this case, fuses rated for 800 amps to 1200 amps should be suitable for most applications. Fusing the primary of the transformer at 125 amps is appropriate to protect the transformer from overcurrent conditions on the primary side. Ensure that the switchgear and fuses are rated for the operating voltage of 2300 volts. Proper coordination between the fuses and the transformer protection devices, relays, should be ensured to avoid nuisance tripping. Follow all applicable electrical codes and standards for the installation of fuses and switchgear. When dealing with the 5 million volt amps, 23,000 volts to 2300 volts delta-delta transformer and planning fuse installation on the secondary side, several crucial considerations must be addressed to ensure safety, proper operation, and compliance with electrical standards. Here's a detailed explanation. Firstly, understand the transformer's ratings. The secondary amperage rating of the transformer at 1200 plus amps signifies the maximum continuous current the secondary windings can safely handle without overheating or sustaining damage. It's a critical parameter for selecting appropriate protective devices. Secondly, fuse selection for secondary protection. Given that the secondary amperage rating is the upper limit, the fuses installed on the secondary side must have a rating below 1200 amps. The purpose of these fuses is to protect the transformer itself, as well as any downstream equipment connected to the secondary side, from overcurrent conditions such as short circuits or excessive load. Thirdly, switchgear bus rating. The 1200 amps rating of the 2300 volt switchgear bus indicates the maximum current the bus can continuously carry without exceeding its temperature limits. It's essential to ensure that the total current flowing through the bus does not exceed this value to prevent overheating and potential failure. Fourthly, fuse arrangement and distribution. A practical approach is to distribute the secondary current into multiple feeds, each protected by its own fuse. The suggestion of using 6 400 amps fuses downstream of the switchgear bus is a viable option. This arrangement allows for a more manageable distribution of the current and provides selective coordination. Each 400 amps fuse protects its respective feed, isolating any faults to that particular circuit without disrupting the entire system. Fifthly, main disconnect switch. Installing a main disconnect switch upstream of the fuses is crucial for safely isolating the transformer from the incoming feed. This switch allows for maintenance, testing, and emergency shutdowns without the risk of electrical hazards. The disconnect switch must be rated to handle the full voltage and current of the secondary circuit. Sixthly, fuse rating selection. The selection of the fuse rating should be based on the actual load current of the downstream equipment connected to each feed. Electrical codes typically recommend that fuses be rated between 125% and 200% of the continuous load current. For general loads, using fuses rated for 800 amps to 1200 amps might be suitable, but this depends on the specific load requirements of each circuit. It's important to perform a load calculation for each feed to determine the appropriate fuse size. Seventhly, primary fusing. Fusing the primary side of the transformer at 125 amps is essential to protect the transformer from overcurrent conditions originating on the primary side, such as faults in the primary windings or upstream equipment. The primary fuse rating should be coordinated with the transformer's impedance and thermal characteristics to provide adequate protection without nuisance tripping. Eighthly, voltage ratings. It is vital to ensure that all switchgear components and fuses are rated for the operating voltage of the system, which is 2300 volts in this case. Using components with lower voltage ratings can lead to insulation breakdown, arcing, and equipment failure. Ninthly, fuse coordination. Proper coordination between the fuses on the secondary side and any overcurrent protection devices such as relays on the primary side is essential to prevent nuisance tripping. Coordination studies should be performed to ensure that the fuses and relays operate in a coordinated manner, isolating faults quickly and minimizing downtime. Tenthly, compliance with electrical codes. All electrical installations must comply with applicable electrical codes and standards such as the National Electrical Code, or NEC, and local regulations. These codes provide detailed requirements for the installation of transformers, switchgear, fuses, and other electrical equipment, ensuring safety and proper operation. Consider the transformer impedance. The transformer's impedance plays a crucial role in limiting fault current. A higher impedance will limit the fault current, reducing stress on the transformer and downstream equipment. The impedance should be considered when selecting fuse sizes and ratings to ensure proper protection. Also, perform a short circuit study. Before installing any fuses or switchgear, it is advisable to conduct a short circuit study to determine the maximum fault current that the system can experience. This study will help determine the appropriate interrupting rating of the fuses and ensure that they can safely clear any faults without failing. Additionally, consider the ambient temperature. The ambient temperature in the location where the switchgear and fuses are installed can affect their performance. High ambient temperatures can reduce the current carrying capacity of fuses, so it's important to select fuses with appropriate temperature rating factors. Furthermore, think about ventilation. Ensure that the switchgear enclosure has adequate ventilation to prevent overheating. Overheating can reduce the lifespan of the switchgear components and increase the risk of failure. Also, consider regular maintenance. Implement a regular maintenance program for the switchgear and fuses. This program should include periodic inspections, testing, and cleaning to ensure that the equipment is in good working condition. Consider infrared scanning. Use infrared scanning to detect hotspots in the switchgear and electrical connections. Hotspots indicate loose connections or overloaded components, which can lead to failures if not addressed promptly. Additionally, consider surge protection. Install surge protection devices, SPDs, on both the primary and secondary sides of the transformer to protect against voltage surges caused by lightning or switching events. Surges can damage the transformer and downstream equipment if not properly suppressed. Furthermore, consider harmonic distortion. Harmonic distortion in the electrical system can cause overheating of transformers and other equipment. If harmonic distortion is present, consider installing harmonic filters to reduce the distortion and improve the system's performance. Also, consider load balancing. Ensure that the load on each phase of the transformer is balanced to prevent overheating and voltage imbalances. Unbalanced loads can lead to reduced efficiency and increased stress in the transformer. Additionally, consider power quality monitoring. Implement power quality monitoring to continuously monitor the electrical system for voltage sags, swells, and other power quality disturbances. This monitoring can help identify potential problems before they cause equipment failures. Furthermore, consider emergency preparedness. Develop an emergency preparedness plan that outlines the steps to be taken in the event of a transformer failure or other electrical emergency. This plan should include procedures for isolating the transformer, notifying emergency personnel, and restoring power to critical loads. Also, consider documentation. Maintain accurate documentation of all electrical equipment, including transformers, switchgear, fuses, and protective devices. This documentation should include equipment ratings, installation dates, maintenance records, and any modifications made to the system. Additionally, consider training. Provide training to personnel who operate and maintain the electrical system. This training should cover the safe operation of equipment, troubleshooting techniques, and emergency procedures. Furthermore, consider grounding. Ensure that the transformer and switchgear are properly grounded to provide a safe path for fault currents. Proper grounding is essential for protecting personnel and equipment from electrical hazards. Also, consider arc flash hazard. Perform an arc flash hazard analysis to determine the potential arc flash hazards in the electrical system. This analysis will help determine the appropriate personal protective equipment (PPE) required for working on energized equipment. Additionally, consider remote monitoring. Implement remote monitoring of the transformer and switchgear to continuously monitor their operating conditions. This monitoring can provide early warning of potential problems and allow for proactive maintenance. Furthermore, consider environmental conditions. Take into account the environmental conditions in which the transformer and switchgear are installed. Factors such as humidity, temperature, and corrosive atmospheres can affect the performance and lifespan of the equipment. Also, consider redundancy. If the transformer supplies critical loads, consider providing redundancy by installing a backup transformer. This will ensure that power is available even if one transformer fails. Additionally, consider future expansion. When designing the electrical system, consider the potential for future expansion. Ensure that the transformer and switchgear have sufficient capacity to handle future loads. Furthermore, consider energy efficiency. Select energy-efficient transformers and switchgear to reduce energy consumption and operating costs. Energy-efficient equipment can save money over the long term. Also, consider life cycle cost. When evaluating different equipment options, consider the life cycle cost, which includes the initial cost, operating costs, and maintenance costs. This will help you make a more informed decision about which equipment to purchase. Additionally, consider supplier reputation. Choose reputable suppliers who provide high-quality equipment and reliable support. A good supplier can provide valuable assistance with equipment selection, installation, and maintenance. Furthermore, consider warranties. Review the warranties offered by different suppliers to ensure that you are adequately protected against equipment failures. A good warranty can provide peace of mind and reduce the risk of unexpected costs. Also, consider insurance coverage. Ensure that you have adequate insurance coverage to protect against losses due to equipment failures or other electrical incidents. Insurance can help cover the cost of repairs or replacements. Additionally, consider regular audits. Conduct regular audits of the electrical system to identify potential problems and ensure compliance with safety regulations. Audits can help prevent accidents and improve the overall performance of the system. Furthermore, consider continuous improvement. Implement a continuous improvement program to identify opportunities for improving the safety, reliability, and efficiency of the electrical system. Continuous improvement can lead to significant benefits over time. Also, consider stakeholder engagement. Engage with stakeholders, such as employees, customers, and regulators, to gather feedback and address concerns about the electrical system. Stakeholder engagement can help build trust and improve relationships. The key is to conduct regular insulation resistance tests. Insulation resistance tests, often performed with a megameter, assess the integrity of the transformer's insulation. Deteriorating insulation can lead to failures and safety hazards. It is also important to conduct turns ratio tests. Turns ratio tests verify the transformer's turns ratio, ensuring proper voltage transformation. Discrepancies can indicate winding faults or damage. In addition, perform winding resistance tests. Winding resistance tests measure the resistance of the transformer's windings, identifying loose connections or damaged conductors. Furthermore, conduct core insulation tests. Core insulation tests assess the insulation between the core and the windings, preventing grounding faults. Also, perform oil analysis. For oil-filled transformers, regular oil analysis is essential. This analysis checks for contaminants, moisture, and other indicators of transformer health. Additionally, conduct dissolved gas analysis, or DGA. Dissolved gas analysis, or DGA, is a specialized oil analysis technique that detects gases dissolved in the oil, indicating potential internal faults such as overheating or arcing. Furthermore, check for leaks and physical damage. Regularly inspect the transformer for leaks, corrosion, and physical damage. These issues can compromise the transformer's integrity and lead to failures. Also, monitor temperature and vibration. Monitor the transformer's operating temperature and vibration levels. Excessive temperature or vibration can indicate overloading or mechanical issues. Additionally, ensure proper cooling. Ensure that the transformer has adequate cooling to prevent overheating. This may involve checking fans, radiators, and other cooling components. Furthermore, verify proper loading. Verify that the transformer is not overloaded. Overloading can lead to overheating and premature failure. Also, check for loose connections. Check for loose connections in the transformer's wiring and terminals. Loose connections can cause overheating and voltage drops. Additionally, inspect bushings and insulators. Inspect the transformer's bushings and insulators for cracks, damage, or contamination. Damaged bushings and insulators can lead to flashovers and failures. Furthermore, verify grounding connections. Verify that the transformer's grounding connections are secure and properly sized. Proper grounding is essential for safety and protection against faults. Also, check for proper ventilation. Check that the transformer has proper ventilation to prevent overheating. Blocked vents can reduce cooling efficiency.